Hi folks, today we're going to discuss the article entitled, Why Should I Trust You? Explaining the predictions of any classifier. This is also known as the L.I.M.E article, and it was published in August of 2016 by Marco Tullio Ribeiro, Samir Singh, and Carlos Gestrin, and it's been cited over 11,400 times. To understand this article, one way to do it is to think about problem spaces, and that is, how do you solve problems? So let's take the problem of how to vacuum a room. So one way to solve this problem is to map out the room and then have your vacuum cleaner follow out this mapping. And that's how, for example, a lot of commercial robotic vacuum cleaners actually work. And this is really known as a deterministic problem or a deterministic problem space. And really, to understand this, it's really kind of the concept that everything's preordained. In contrast, let's look at the problem of moves in chess. So in chess, there are 10 to the 43 legal moves, meaning there are more legal moves than there are atoms in the universe. And this is known as a stochastic problem. And so when you're dealing with stochastic problems, you really need to have what's called a probabilistic strategy. So for the purposes of this presentation, our problem space is going to be how to determine a dog by looking at a photo. In particular, we're going to be looking at the size of images versus the number of dog-like features. So in the lower left-hand part of this space, we're going to have low resolution photos with few features. So these are going to be photos where you can just barely make out, say, a snout, an ear, or a tail. Whereas in the upper right part of this space, we're going to have high resolution images where you can make out many features such as floppy ears, pointy ears, curly tails, fur, or various colors of eyes, for example. And so this problem space, because of the various permutations and combinations of potential features of images, this is going to be a stochastic space, and hence we're going to need a probabilistic strategy to solve whether or not a photo is of a dog or not. Okay, what are some strategies to determine whether a photo is of a dog or not? Well, one strategy may be to identify a set of photos you know to be of dogs. Identify features from this set of photos, we'll call that a training set. Identify a photo and features associated with that photo to compare and contrast against this training set, we'll call that the test set. And then to generalize the features of the training set by comparing the differences in distance values between the training set and test set features. This strategy is known as k-nearest neighbor, KNN. And the way this works is that you, again, identify a set of dog photos, take features from that set of dog photos and put them into a table. So you'll have a table basically where each row represents a photo, and then you have features associated with each of those photos in the form of, for example, the location of a snout, an ear, or a tail in the photo, and then you'll label that photo as to whether or not it's a dog or not, with 1 being that it is a dog, 0 being not a dog. And so that'll really constitute your training set. Next, you'll create a test set by taking a photo, and from that photo, basically identifying features such as, for example, a snout location, ear location, tail location, and then the label will be unknown because you're going to need to determine whether or not that photo is of a dog or not. And then what you'll do is you'll compare the difference in distances between the test set and the training set. So here we basically take values from the training set of, say, for example, 2, 4, and 3, 5, and we determine the difference between those values and the values of the test set of 2, 4, 3, 5. And here the result is, and in terms of distance, is 0. Thus, that means that the test set photo is that of a dog. All right, let's look at some problems with KNN as a strategy. The first is that KNN relies upon separation between training sets. Well, what does that mean? That means that if I introduce into the problem space, for example, hyena photos that are low resolution, hyenas share many of the same features as dogs do. They have snouts, they have ears, they have tails. Similarly, if I introduce wolf photos into the problem space, well, wolves share many of the same features as dogs, and so it's going to be tough to differentiate the two. If I introduce werewolves, same problem, that werewolves share many of the same features with dogs, so it's going to be tough to differentiate them. But here's another problem that maybe didn't occur to you. Photos with different orientations are going to actually be required to be inputted into the training set separately, because even though the photo looks the same, once you change the orientation of the photo, that actually results in being new features that have to be considered. And this is the concept of spatial indifference. And some AI/ML models are very good at handling spatial indifference, others are not. KNN is an example of one that isn't. Another problem that you have to deal with is that all of the data needs to be pre-labeled. So all of the photos need to be labeled such that a table is created reflecting the features of the photo and then basically a class label as well. And someone has to do that, and that's time consuming and takes a lot of work. And really what this all goes to is that the world is a messy place. So what do you do given the fact the world is messy? So what's a strategy for dealing with the messiness of the world and determining whether or not a photo is of a dog or not? So maybe one strategy is that you identify a set of photos, some of which you know to be dogs. You label features and classes, that is, you structure the data associated with these photos, and you insert that data in a table, much like you do with KNN. And then you build ensembles of decision trees reflecting subspaces, where these are subspaces of your overall problem space. And these decision trees are built using randomly generated sets of data. We'll call this the training set. And then finally, for determining whether or not a photo is actually that of a dog or not, you basically have each one of the decision trees effectively vote on whether the test photo or the test set is that of a dog or not. So that's a lot to understand, so let's unpack it. So first of all, this is known as a random forest strategy and is well known in the field of AI/ML. So the way this works generally is that you have your problem space and you take your problem space and you subdivide it into smaller problem spaces. And for each one of those problem spaces, you solve the problem of whether or not the photo is of a dog or not. So let's see how this works actually in practice. Okay, so you're given a set of photos, some of which you know to be dogs. So much like KNN, what you're going to do is you're going to take these photos and extract various features from these photos and put them into a table. So here we have a table of various photo sizes. Some of the photos are 32 by 32, some are 1024 by 1024. Some of the photos have snout, ear, and eye color, some don't, some have fur, some have pointy ears, floppy ears, curly tails, etc. So you're going to take all of these features, put them into a table, and then for each one of the photos, you're going to label it as to whether or not it's a dog or not. So the class label here is going to be 1 for if it's a dog, or 0 if it's not going to be 0. So you have your table. The next thing you're going to do is determine the number of subspaces that you're going to have within your space. And each one of these subspaces is going to correspond to a particular decision tree in your random forest. And so you can have 100 decision trees, you can have 1,000, it's really up to you, but each one of those decision trees is going to correspond to a subspace, which is going to be based upon a data set. So let's talk a little about how the data set's created. So the data set's going to be created by taking at least 66% of the table and putting that into a decision tree, and then randomly selecting the remaining 33% from the total data set. So that randomly selected portion is going to be basically randomly selecting a photo and all of its associated features. And you're going to do that for each one of the decision trees. So here we have basically 5 subspaces and 5 sets of data. And then from that, again, we're going to generate decision trees. And these decision trees are really going to have data around the particular features of the photo. So you're going to have within a decision tree, for example, the features of eye color, tail, floppy ear, snout, ear, tail, etc., etc. Once you have your random forest built, then you're going to take a test set or a test image and pass it into each one of the trees in the random forest. And so each one of those trees then is going to basically vote on whether or not the image is of a dog or not, and those votes will be tallied, and then finally a determination will be made whether or not the photo is of a dog or not. So here, for example, after we pass the test set in, that vote by a vote of 2 to 1, the determination is made that it's of a dog. One of the problems with the random forest is that much like KNN, it requires that you take a photo, extract features from that photo, and put those features into a table. And that's really time consuming and takes a lot of effort. And so while random forest is good at handling the messiness of the world is also unstructured. So what's a good way to handle this unstructured nature? So given the unstructured nature of the world, what's another strategy that you can employ to determine whether or not a photo is of a dog or not? Well, one strategy is to identify a set of photos, some of which you know to be dogs. Trust that there is an inherent probabilistic relationship between pixels in this set of photos and that these pixels are indicative of whether or not the images are of that of a dog. We'll call this a training set. And then provide another photo as a test set to determine whether or not the test set and the probabilistic relationship between pixels therein are similar or the same as the probabilistic relations between the pixels in the training set. So to unpack this a bit, this is how a binary neural network classifier works. And the way you train this is you pass in a set of photos that you label those photos as 1. So you pass in basically an X value, which is the set of photos, and a Y value for each one of those photos set to 1, where 1 is indicative of the photo being that of a dog. And what the binary neural network classifier will do is that it'll engage in edge detection. That is, it'll determine basically the statistical correlations between pixel values in the photos and what those statistical correlations tell you regarding the edges and values within those photos, and that those statistical correlations will be learned. So in other words, the network will really determine the edges, the outline, the snouts, the ears, the tails, and ultimately the complete image of the dogs, and it will learn those values. Once the neural network is trained, the next step is to test it. And so testing can be done by taking unstructured data in the form of an image, passing this image into the neural network, and the neural network will determine whether the image is of a dog or not. So put another way, given a learned training set, Y is the statistical probability that the input X is a dog. And this can be represented as the probability of Y given an X, where Y is 1, which means dog, or 0, which means not dog. What are some problems with neural network classifiers? A first problem is that the high degree of freedom that these classifiers manifest can result in them generalizing the wrong features. Another problem is that of opaqueness. With respect to this issue of generalizing the wrong features, take, for example, the case of a neural network classifier that determines whether or not an image is of a wolf versus a husky. So shown on the left is an image of a wolf. Shown on the right, however, using L.I.M.E, we see that the neural network classifier is generalizing a background snow as opposed to features of the wolf to determine whether or not the image of a wolf is of a wolf or not. This is particularly problematic if we're talking about such things as a neural network classifier that determines whether or not an X-ray depicts a cancerous tumor, or say another neural network classifier that determines whether or not someone is a suspect in a crime or not. Another problem with neural networks is the problem of opaqueness. If you remember, random forests basically showed you the outline of the data structure or the decision process that was used to determine whether or not a photo was, say, of a dog or not. And this is something that was visible and you could actually print out and show to basically explore the decision process. By contrast, neural networks are relatively opaque insofar as that compared to random forests, there's no easy linear explanation for how certain decisions are made within the neural network. So you can see this highlighted portion, you see that there's multiple inputs, one output, but really how the decision process works from a linear perspective is a little opaque or unknown relative to, say, for example, random forests. A solution to the opaqueness of neural networks in any other AI/ML model comes in the form of L.I.M.E. L.I.M.E stands for Local Interpretable Model-Agnostic Explanation. And so the way this works from a strategy perspective is that you take a problem space and you reduce that problem space from a global set of predictions made by a classifier to a collection of subsets. And then you sample basically pixel values that are close proximity to the pixel values predicted by the AI/ML model on a global level. And then you basically determine the difference between the local predictions and the global predictions made by the AI/ML model. And if there's a large difference, then you can come to the conclusion that the AI/ML model may be generalizing on the wrong features. So let's see how this works. So imagine an image of a dog, and you take basically an exploded view of that image of a dog, and you basically then have one function, which we'll call f of z. And f of z will basically be a localized prediction of what, for example, a pixel value ought to be. Whereas g of z prime is basically the generalized value of another pixel value that's in close proximity to that first pixel value. And then what you'll do is you'll find the difference between the two. And if there's a large difference, then this can indicate basically that the AI/ML model is generalizing on the wrong set of features. About a year after the L.I.M.E article came out, another article came out entitled Explainable Artificial Intelligence, Understanding and Visualizing Interpreting Deep Learning Models. And so this article proposed something called L.R.P. So to understand L.R.P, we need to go back and talk a little bit about how neural networks actually classify images. So previously I had said that neural networks classify images by basically attaching a 0 or 1 value as an output of the neural network. In actuality, if you look at it from a more fine-grained perspective, the output is usually something more along the lines of, like, say, 0.8, that the image is, say, of a dog, or 0.2, the image isn't of a dog. And that's because each one of the nodes in the neural network actually outputs a probability that an image is or is not of a particular class. So for example, a node may output 0.7, or that there's a 70% chance that the image is of a dog, or say 0.4 or 40% chance that the image is of a dog, or even 0.3 that there's a 30% chance that the image is of a dog. And so what you can do is that you can basically backtrack or effectively work backwards from the final decision that's made by the classifier to each of the nodes that made the decision ultimately in a particular layer as to whether or not the image was of a particular class or not. And so the advantage of this approach using L.R.P is that it creates a linear description of the decision process for a neural network. And that's something that makes these decisions of a neural network less opaque, more understandable, because it kind of converts the decision process into a linear process that's, again, more easily understandable. Another thing that it allows for, though, is it allows for the optimization of certain neural network models by identifying those nodes that make decisions that are optimal for the particular problem space that you're functioning in. So what you can actually do is identify nodes and then propagate those nodes and create new versions of those nodes where those nodes manifest behavior that you want in terms of their classification abilities. And this is a really good way to kind of optimize your neural network. Summing it up, what does your problem space look like? Is it deterministic or stochastic? If stochastic and a probabilistic solution required, then is the space clean? Is there good separation between your data, or is it messy? If messy, then how explainable is your AI/ML solution? L.I.M.E and L.R.P provide ways to begin to explain your solution to ensure it is generalizing on the correct features. I hope you've enjoyed this presentation.